You might just have seen the derivation, the proof of the quotient rule. The quotient rule tells us how to differentiate a quotient of functions. It means that if you have a function g of x given by f of x over g of x, the derivative of f of x over g of x is given by the derivative of f of x times g of x minus the derivative of g of x times f of x divided by g of x squared. We've seen the proof, so we believe it. Therefore, it means we can apply it, and whenever we're dealing with quotients of functions, we don't need to calculate those very complicated limits. We can just use it. This is the perfect opportunity to actually try it in practice. We'll start with a simple example that you can also find in the lecture notes. In section 5.2.6, this is example number 1. We want to differentiate g of x, which is sine of x over x squared. When you look at a function like this, and in general terms, you'd recognize that you're looking at quotients, and therefore, in order to use the quotient rule, you need to identify which one is fx, which one is g of x. In this case, we can say that f of x is sine of x, and g of x, you can identify it as x squared. If you want to apply the quotient rule, you already have 2 of the ingredients. The other ingredients you'll need is the derivative of f of x, then derivative of g of x. We haven't really demonstrated from first principles that the derivative of sine x is cos x, but you can go along with it now. We will demonstrate that the derivative of cos x is minus sine of x from first principles. This implies that the derivative of f of x is cos x. You can try determining it from first principles. Actually, you have all the tools, and get in touch if you want to do that. And also note that whenever I'm doing these examples, and also the way I wrote them in the lecture notes, is to teach you the level of detail and explanation that is expected from you, for example, in a worksheet to get full marks. For g of x, it's even simpler. The derivative of g of x is just 2x. You drop the exponent and you get it. Minus 1 is 1. By convention, we don't really write it. It means we have all the ingredients, so we just have to put it in the formula. This implies that j, the derivative of j of x, is equal to cos x times g of x, which is x squared, minus the derivative of g of x, which is 2x, times f of x, which is sine x. And you're dividing by x squared to the power of 2, which will be x to the power of 4. So when you do this, it's the same as this. So you get x to the power of 4. If you're really lazy and sloppy, you could leave it like this. You probably wouldn't get the full marks because there is an easy simplification step that you can do, which is to realize that all terms have an x. It means you can cancel this out. This becomes just 1, and in this case it becomes 3. And therefore we can write that the derivative of j of x is cos of x times x minus 2 sine x over x to the power of 3. We did it then. But let's try another example. Something that probably you wouldn't think about using the quotient rule, but you can. And this is a very good example about the fact that a lot of functions, you can sometimes transform them to then use rules that you are very familiar with. Let's try it. The other example that you have in the lecture notes, following the one that we just did, is to differentiate function j of x equals tangent of x. Maybe you already know what this derivative is, and that will be okay going forward in Physics 101 and all the physics modules. But for now, let's try to differentiate this using the quotient rule. The trick really is to identify which is f of x and g of x. In this case, we know that we can write tangent of x as the ratio between sine x and cos x. This means that we can identify f of x and g of x. In this case, f of x is sine x, g of x is cos of x. Therefore, all we have to do is differentiate the individual functions. The derivative of f of x, as we've seen in the previous example, is cos of x, and the derivative of g of x, and we'll prove this from first principles, it's minus sine of x. It means we now have gathered all the ingredients, so we can calculate the derivative, and we can write that the derivative of j of x is equal to the derivative of f of x times g of x. And again, I'm doing this very slowly to make sure that no one is left behind. If you're already a pro at this, that's great. You can move on and go to more advanced examples. But if you're struggling with some details, I really want to make sure that I don't lose you. That's why I'm trying to explain every single detail. We don't really have space to write the rest of it. Let's use some new Physics 111 magic, which is to try to move this over there using the force. Looks like it works. So we now have proper space to write the solution, which means we can write that the derivative j of x is equal to the derivative of x times j of x. We look here, this is the derivative, and we're going to time it by cos of x. We end up getting cos of x squared, and then we need the derivative of g of x times f of x. In this case, it's minus sine x times sine x. Because we have a minus, these will cancel and become plus. So we can write sine square of x, and then we're dividing by g of x squared, which is cos of x, which is cos of x squared. What we can do here, very simply, is to recap, and this is another call. If you haven't done so, look at the background material, including trigonometric identities, which we can use here, as we know that cos squared x plus sine squared x is equal to 1. We're going to convert this into 1 to get 1 over cos squared x. Finally, we can recognize that 1 over cos x equals the secant of x, and therefore the square equals secant squared of x. And this would be the final answer. Of course, maybe you already know that the derivative, a tangent of x, is secant of x to the power of 2. But in this case, this was a nice demonstration of how you can use the quotient rule, even when a function doesn't look like a quotient. You do need, of course, to practice a lot, and also a lot of the functions won't be as trivial as this one, and you will not just be given a statement like use the quotient rule to find the derivative of this function. You'll get a function where you will have to use quotient rule, product rule, sum rule, all of them together, including the rule of all rules, which is chain rule, which we haven't covered yet, but we will very soon.